In this lecture, you will learn about solution to one problem where it asks that you are given a graph G, V, comma, E, where V is the vertices and E is the set of edges. So now you are asked that okay, a source node is given and you are also given a destination node. And it says that describe an efficient algorithm that determines an optimal path from S to T given your preference for stopping at U along the way if it's not too inconvenient. Okay, so it says that okay, you have to go from source to destination T. Okay, so there should be a shortest path. But it also says that you can stop. Okay, so if it's okay to take a rest, and then what you need to do, you have to go via U. But the thing is, you can rest here only when there will be only an additional length increase of 10%, I think. So it says that this algorithm should either return the shortest path from S to T or shortest path from S to T containing U, depending on whether or not the latter is convenient. Okay, so convenient here says I think it was 10% increase in path. Okay, so either I go from S to T directly. Okay, so not directly, but it's not necessarily using U. If it comes, then it's fine, but I'm going from S to T, shortest path I will run any of the shortest path algorithm, or otherwise I have to go take rest at U and then from U I move to T. So this is the question. So rather than designing your own algorithm from scratch, use one of the already known algorithms as subroutine. So it also says that you can think of some already existing shortest path routines which you can use. In this way it becomes easy. So this is the hint. So now let's try to solve this problem. So one thing that we should note is that shortest path problem has optimal substructure. Okay, for shortest path. So what it means is that let's say we have a graph, okay, and this is the shortest path from S to T. Now if there is some node here, okay, so V is another node in the shortest path. So this is S, this is T, there are other nodes V1, V2 and V3. There are many more, but there are some nodes which I have marked. Okay, so now it says that okay, if this is the shortest path from S to T which contains V1, V2, V3, then S to V1 is also the shortest path, V1 to V2 will also be the shortest path, V2 to V3 will be also shortest, and V3 to T. This is because let's say think. So S to V, let's say shortest path, it's 2 and there it is 3, V to T. This is the shortest path, total length is 5. So now what happens if there was some other if this was not the shortest path from S to V, and let's say there was some other shortest path which has cost 1, then what will happen? This is a kind of contradiction, because then this will be the shortest path of length 1 from here, because it decreases the length by 1, it becomes 4. So your shortest path, even the sub paths of the shortest paths are shortest paths. So even if we stop somewhere, so this part of the path will be also shortest, this part of the path will also be the shortest for shortest path. So it says if V is in the shortest path from S to T, then distance S to V, distance V to T are also the shortest path from S to V and V to T, okay, which we proved. Now what it says, now in our question, let's assume that okay, so we will assume that okay, U does not lie on the shortest path. If it lies, then there is only one path, U lies on it, then there is no problem. But if U does not lie on the path, we need to find the shortest path from S to T, where it says that okay, you can directly take the shortest path from S to T, or you can go via, so this is the shortest path I can take, but I want to take rest, then I will go from S to U, U to T, and if this distance ds ut is not increasing by more than 10% of ds comma t, then we will take this path. Okay, so then shortest path P is given by minimum of ds comma t into 110 by 100. So this is just incrementing by 10%. If okay, so if at our distance while going from U so what will be the shortest path if I have U in between? The shortest path will be the shortest path from S to U and then the shortest path from U to T. That will be the shortest path from S to T if I have to stop at U. So the shortest path, this is also important, shortest path from S to T if I am going via U will be ds to U, then du to T. These are the shortest path from S to U and du to T. So now what I do it with your shortest path will be, I will just compare minimum among ds to T 110 by 100 or 110% of this, and or it will be the sum of ds comma u du comma T, where ds comma u du comma T, they are all found by some shortest path algorithm which we already have. So let's say we are using Dijkstra's algorithm. So where dst, ds comma u comma T are obtained using some shortest path algorithm. For example, in our case we will take Dijkstra's algorithm. Now time complexity of Dijkstra's algorithm for GV is O of E log V. So this is mod E tells is the number of edges in our graph, and log of mod V is the number of vertices. So this is the time complexity for Dijkstra's algorithm. Now what we are doing in our algorithm is, so this is the function Dijkstra's, it gives the graph, you give it as input weight of the edges and the source node, and then what does it find for you? It will make an array where you have a kind of map d v1 d v2. These will be the shortest path length from the source to these nodes, okay, and parent of v1 will be the parent from where we come to the next, this v1, okay. So this is there, it fills all these, and then you can easily find, okay, for if I example I want to find the shortest path from S to T, I will find dt after running Dijkstra's gw comma s, okay. So this will give d min s comma T. If I run with source as S, it will give d minimum distance from S to T, minimum distance from S to U. Those can be obtained from here. Now again run Dijkstra's algorithm. This time I will run with source node as U. So now what will happen? This will give me distance from, shortest distance from all nodes from source node U. So now what I want this will give me, the first call will give me ds comma T. It will also give me ds comma U. When I run this one, it will give me du comma T, okay. So this way now I have ds comma T. From our previous one I will multiply it by 110 by 100. Then I also have ds comma U. I first go from S to U, then I go from U to T, and whichever is the minimum I will take that path. So that's there. Now if U is already there in the path from ds to T, then there is no problem, there will be only one answer. And in fact even then if you run, so this one and ds to U, du to T, okay, so they will be, so this one will be smaller because it because this dst will be equal to dsu comma dut, okay. So this is about, and how we prove that, okay, we will have a shortest path. So let's see what was the question. So time complexity. Now let's think about the time complexity. I was running Dijkstra's algorithm twice, so this is just a factor of 2 times I will run, so it will be again O of E log V times, it will be the same as the complexity of Dijkstra's algorithm because I'm just running it twice. And what else? So now why is it correct? Proof of correctness. So let's see the question, I think. So let's see. So what is the running time of your proposed algorithm and why? So running time is again same as Dijkstra's algorithm. Why? Because we are just running it twice for different sources. Argue that your algorithm is correct. It indeed gives you a shortest convenient path, okay. So why is it correct? So let's try to see that. So it's correct again because of, so you can just write because of optimal substructure of shortest path. So this is optimal substructure of shortest path. Because of this it will give us, because again when I'm going from S to U and from U to T, so these are again the shortest path, because shortest path plus shortest path will be the overall shortest path. So that's why in for convenient this shortest distance also this will be fine. So I hope you understand this. Thanks a lot.